Alright, this lesson is all about the independence of events in probability. Alright, will the two events be dependent or are they independent? Because that affects how we calculate the probability. But first, real quick, let me try to give you just a general understanding of what it means for two events to be independent. Let's say you're going to flip a coin twice. Okay, you're going to flip a coin twice. Alright, let's call event A. Let's let event A be heads. Okay, on heads on the first flip. Okay, and let's let event B be heads again. Alright, so heads, event A, we're talking about the first flip. Okay, now what's the probability of event A? Alright, if you flip a coin, what's the probability that it's going to turn up heads? Yeah, that probability is 1/2, 0.5, 50%. Okay, now let's say that the first coin did turn out to be heads. So now we're going to flip the coin again and go for event B. Now, what's the probability that the second flip is going to turn out to be heads? Yeah, we're still flipping a coin, alright? You still have a 50-50 chance that it's going to be heads. So the probability is still 1/2. So the deal is these two events are considered independent because if the first coin turns out to be heads, the second coin has a probability of being 1/2. But what if the first coin turned out to be tails? Doesn't matter, alright? The probability of the second coin being heads is still 1/2. It doesn't matter whether the first event happens or not. It doesn't change the probability of the second event. Okay, so those are called independent. Now, what we find is that when two events are independent, then the probability of both of those things happening, okay, the probability that event A and event B are both going to happen is the same thing as the product of their individual probabilities. Okay, probability A times probability B. Alright, this will only happen if they are independent. So just keep this in mind as well. If their probabilities do not, if we had two probabilities and we multiplied them together and it didn't equal their intersection, then by definition they would not be independent. Anyway, the probability of A and B, which I'm just showing that I could write it either way, would be 1/2 times 1/2, which would be 1/4. Okay, so there's a 25% chance that both of these two things will happen. Okay, so anyway, that's when it's independent, when the first event happening does not affect the probability of the second thing happening. Now, let me give you an example where the two events are dependent. Alright, let's say we had a bag of marbles. And in that bag, we have 7 yellow marbles and 3 red marbles. Okay? Let's let event A, because our plan is to pull out 2 marbles. Okay? Let's let event A be pulling out a yellow marble. I'm sorry, let's let event A be pulling out a red marble. Okay, first. and we'll let event B be pulling out another red marble. Second. Okay? Now, let's see if these two events are independent or if they are dependent. If they're independent, then the probability of event B, it won't matter whether event A happened or not. Okay? So let's check and see. To be clear, we are pulling out two marbles in a row without replacing. Now, look out for that phrase to show up over and over again. Usually, if we are not replacing what we're taking out, then that's definitely going to change the probability, and you're going to have a dependent event situation. So let's think about what the probability of event A is. That was the probability of pulling out that first red marble. Well, target over total, okay? It's the number of favorable outcomes divided by the sample space. So, if I want red marbles, if I want to pull out a red marble, there are 3 targets, all right, the red marbles, out of a total of 10. So my probability of event A is happening is going to be 3 out of 10. Okay? Now, so let's say event A happened. So that means we pulled out a red marble. And we are not replacing it, so it is out. So when we go to do event B, what is the probability of event B? Okay? So the probability of event B, given that event A already happened, all right? Assuming that event A happened, then the probability of that event B, we're looking at it. There are 2 red marbles left, and out of a total now of 9. Okay, so the probability is 2 out of 9. Okay, so that's one scenario. Now, what would the probability of event B, what would it have been if event A never happened? Now, if event A never happened, then the probability of pulling out a red marble would have been it would have been 3 out of 10. Okay, because there's 3 red marbles and 10 marbles total. Now, what if when you pulled out that first marble, it wasn't a red? What if it had been a yellow? Okay, so imagine that the first, for event A, we were shooting for a red. But what if it didn't turn out to be a red? What if it had been a yellow? Would that affect the probability of event B? So let's imagine the probability of event B, okay, given that the first marble we pulled out was yellow. Well, in that case, the probability, there are still 3 red marbles to pick from, but there's only a total of 9. So as you can see, the probability of event B depends. If event A happened and we pulled out a red marble, then it's 2 out of 9. If event A didn't happen and we pulled out a yellow marble first, then it would be 3 out of 9. Okay, if we didn't pull out a marble at all, then it would have been 3 out of 10. So event B definitely depends on whether event A is happening or not. So that is what you call a dependent situation. Okay, it is not independent. Alright, now you can still calculate the probability of event A and event B happening. But the probability of A and B happening will be the probability of event A times the probability of event B after we take into account that event A already happened. In other words, after we change the numbers to reflect what happened in the first event. You know, going back to the earlier situation, hush phone, where if event A happened and we took out a red, we can still multiply these two probabilities to figure out the probability of both things happening. But the probability of A was 3 out of 10. Now the probability of B, after we take out that first red marble, is 2 out of 9. So we'll have to do 3 out of 10 times 2 out of 9. And so that would be 6 out of 90, which is going to reduce which reduces down to 1/15. So that would be the probability. Alright, let's do a couple problems. Alright, the table shows 4 sets of values for probability of A, probability of B, and the probability of A and B. Based on the definition of independence, determine if events A and B are independent in each case. Alright, well, event A and event B will be independent if and only if the product of probability A and probability B equals the probability of A and B. So if we multiply these two numbers, let me zoom in. If we multiply these two probabilities together, the individual probabilities, and that equals the probability of both of them happening at the same time, then by definition they are independent. So let's do 0.2 times 0.14. Okay, so 0.2 times 0.14. That is, hold on, that is 0.028. 0.028. So, yes, they are independent because this times this does equal that. Alright, what about the next one? Okay, can I scoot over a little bit? Yeah. So 0.32 times 0.16. Let's see if it equals 0.48. Alright, that equals 0.0512. Alright, so that does not equal 0.48. So that means that these are not independent, and we could say they are dependent. Okay, this one we should not need a calculator for, because when you multiply two fractions, you multiply straight across. So 1 times 3 is 3, and 3 times 5 is 15. Alright, so 1/3 times 3/5 is 3/15, not 4/15. Okay, so I'm just going to say these are not equal, so no. These are not independent. They're dependent. Let's see, what about this? Again, if I do 7 times 2, that is 14. And 8 times 5 is 40. Alright. Now if I do half of both of these, that gives me 7/20. So they are in fact equal. So yes. Alright, event A and event B are independent in that case. Okay, that was problem number 1. Alright, problem number 2. Using the letters in the state Arkansas. Find the probability of picking S and then A without replacement. Okay, as soon as you see without replacement, just be careful, but know that these are dependent. Okay, those are dependent, not independent. Anyway, so the probability of picking S, okay, first. So let's see, target over total. How many S's are there? There's 2 of them. How many total letters are there? 1, 2, 3, 4, 5, 6, 7, 8. So that's 2 out of 8. That's the first probability. Okay? And then A without replacement. If we picked an S, then they're saying we're taking it away. You know, like the marble that we took out of the bag. Okay, so that S is gone. So now, if we want to calculate the probability of picking out an A on the second turn, well, how many A's are there? There's 1, 2, 3 A's. Out of how many total letters? Well, there were 8, but we're down 1 letter, so it's 3 out of 7. Okay? So, if I multiply these two probabilities together, then that will give me the probability of S and then A. Okay, so that's going to be 6 over 56, and this will certainly reduce. Three 28ths. Okay, so that is the probability of picking an S and then an A without replacement. Okay, let's find the probability of picking a K and then an N, again without replacement. Okay, that means it'll be dependent once again. So let's see, probability of picking a K. So we're starting over. So let's see, how many K's are there? Alright, there's just the one K. Let me just recount. 1, 2, 3, 4, 5, 6, 7, 8. So the probability of picking a K the first time around was 1. Why did I just really put 1 out of K? Alright. 1 out of 8. Now, the probability of picking an N. So the K is gone. We pulled it out. It's gone. So now the probability of picking an N. Well, how many N's are there? There's one N, but now, just making sure that was only N, but now there are only 7 letters left because the K is gone. So these are the two probabilities. So if I want the probability of both of these two things happening in a row, all I have to do is multiply. So that would be 1 over 56. All right, you just multiply straight across. 1 times 1, 8 times 7. So that would be the answer to that, part B. Now, part C. Okay, let's start over. Do they say without replacement again? Yes, again, without replacement. So be careful. Okay, so we're going to pick an R and then an S. So let's see. I see an R. There's only one R. So that's 1 out of 8. Okay. And then an S. So we have 2 S's at this point. So that's going to be 2. But we have 7 letters left because we already pulled out an R. So that'd be 2 out of 7. If I want the probability of both of these things happening in a row, I will multiply. So 1 times 2 is 2. 8 times 7 is 56. This has to be reduced. Alright, it's 1/28. Okay, that's number 2. Let's move on to number 3. I better zoom out. Okay, number 3. A test includes several multiple choice questions, each with 5 choices. Suppose you don't know the answers for 3 of these questions. So you guess. What is the probability of getting all of them correct? Okay, so we have several multiple choice questions. Each have 5 choices. Alright, so what's the probability? Alright, you don't know the answer for 3 of these questions. Alright, what's the probability of getting all 3 correct? So, the probability of guessing the first one correct is 1 chance in 5, because there are 5 choices. Okay, and it's going to be the same thing for all 3. Alright, you know, there's no taking out and replacing like we did with the letters and the marbles in my earlier example. Okay, no matter what, you have 5 choices. Okay, so in each case, the probability is 1/5, 1/5, and again on the third question, if you're guessing, you have 1 chance in 5. So if we multiply all these together, that will be the probability of guessing all 3. So 1 times 1 times 1 is 1. 5 times 5 is 25. Times 5 is 125. Or if you had a calculator, you could just go 5 times 5 times 5. Okay, that's 125. Okay, so that is the probability, is 1 out of 125. Yeah, you could turn this into a decimal if you wanted to. You don't need to, but I'm going to show it anyway. If I did 1 out of 125, okay, toggle it, that's 0.008. So that's 0.8%. Okay, not a really good likelihood. Alright, number 4. The chart below shows favorite subjects of students based on their gender. Answer the questions below based on the information provided. What is the probability that a randomly chosen student likes history the most? Well, when we do probability, we're doing target over total. In this case, our target is history, people that like history. Alright, so how many students like history, and what's the total number of students? Okay, 25 plus 36. Okay, that's 61 students. Okay, so that's 61 students. Okay, I went ahead and calculated all the totals in case we need them. And especially since we need the 240 right now. That's the total number of all of the students on the chart. So we have 61 like history out of a total of 240. Okay, apparently that does not reduce. Let me see if I can move this over a bit. Alright, apparently that does not reduce, so we could just leave it like that. Or we could make it into a decimal, 0.2542. Or we could make a percent, 25.42%. Now, what's the probability that a randomly chosen student is female? Okay, let's see, target over total. Target is now female. Alright, so how many females are there? Well, if we total up this column, there are 114 females. So target over total, that makes it 114 over a total of 240. Okay, so 114 out of 240. Alright, so that reduces to 19 out of 40. Alright, and you could leave it like that, or you could toggle it and get 0.475. Which is 47.5%. Now, what's the probability that a randomly chosen student is male or likes math? Okay, if we're doing or, we're not doing both. Okay, so we're going to highlight all of it. Okay, we're going to highlight all the males, and we will also highlight all the math likers. Alright, so male or liking math. Alright, here's all the males, so let's include that in our target, or people who like math. Okay, now I gotta be careful because I cannot just add up these two numbers. Okay, because if I counted up these two numbers, I would be counting this number twice, because these are the students that are male and they also like math. I'd be counting them twice. So I actually could add the 126 and the 58, and as long as I subtracted the overlapping 46, which is one of the things that we often do. In other words, we could use the formula that we learned, which said that the probability of, male or math, they both start with M, so what should I do? Alright, so using the formula, it would kind of be like this. The probability of male or math would be the probability of male, which is 126, don't have enough space, 126 out of 240, plus a probability of math, which is 58 out of 240, minus the overlapping part, which is minus 46 out of 240. Okay, so if I did that, let's see, 126 plus 58 minus 46. That's 138. Alright, so that would give me 138 out of 240, which I could then reduce. Okay, but another way to look at it is by, oh man, I didn't mean to erase all of that. Let me try that again. Okay, another way to look at it is like this. Let's start with the males. Okay, we want to highlight all the males. We will also highlight all of the people who like math, but we're not going to count anybody twice. But we can start by highlighting all the males. Okay, of course, so far that's 126. I know that. Now, so now we're going to highlight all the people that like math. Now the 46 is already highlighted. I'm not going to count it twice. But in addition to that, I'm also going to highlight the 12. The 12 females who like math. Okay, so all together, I'm going to count up all 5 of these numbers. Alright, well, of course, all the males are 126. So I really just need to do 126 plus the extra 12. Okay, so that's a good way to think about it. Alright, you should be able to do that in your head. But if you have trouble, then again, that's 138. Same thing we got before. So back to thinking in terms of target over total. Alright, so the people that fit this description, male or like math, there's 138 of those people out of a total of 240 students. Alright, so it's time to reduce. So that's 23/40. Whoa, wrong page. Alright, and of course I can make that into a decimal or a fraction. 0.575, which equals 57.5%. Now D. What is the probability that a randomly chosen student likes both science and is male? So when we did or, we just highlighted all of it. But when it says and, we're only going to highlight the cell that indicates both at the same time. Alright, liking science and is male. There's only one cell on this entire chart that represents science and male. Okay, so here's the science column and here's the male row. This is the cell that satisfies both. Alright, science is favorite and male. So target over total, there are only 42 targets, alright, or male science lovers out of a total of 240 students. So we'll just reduce that. So 42 out of 240. That's 7/40ths. Which is 0.175. Which is 17.5%. Okay, just a couple more. What's the probability that a randomly chosen student likes history given that they are female? Okay, there's that expression, given that they are female. When something is given, that tells us that is a fact. It's not a probability anymore. So that is shrinking our universe down to a universe of only females. So given that they are female means we are going to focus our eyes right here on this part of the chart. Okay, we are going to focus on this part of the chart and nothing else. Okay, and it might be helpful to sort of cover up the other parts of the chart, all right, the male part of the chart, because it is now irrelevant. So I'm going to cover up all of that. So when they say given something, you focus on that part of the chart and pretend the rest of it never existed. And then you go back and answer the rest of the question. Alright, now that we have our universe narrowed down to just this row. Okay, so now what were they saying? What's the probability that a random student likes history? Okay, that's what we want to actually know. So, which one of these numbers is the history number? 36. So when we do target over total, we're going to do 36. But we're not going to do out of a total of 240 like we've been doing. Oh no, we've now narrowed the universe down to 114 people, the females. So target over total in a given female situation is 36 out of 114. That's 6/19. That is 0.3158. Or 31.58%. Alright, I keep showing all three of these forms, but you could just leave it as a fraction. Okay, now, I think this is the last one. Alright, it says use calculations. Maybe they mean use a formula. Maybe they mean do it using the formula I was showing you a minute ago. Let's see. Does the probability of liking a subject depend on whether the students are male or female? Use calculations. Okay, so does it depend on? All right, so they're asking you, is this independent? Okay, the probability of liking a subject. Okay, so in other words, we have all these subjects. So what were the subjects we had? Math, science, English, history. Alright, remember the calculations we did way back at the beginning to find out if event A and event B were independent. If the individual probabilities were multiplied, if that equals the probability of A and B, then they're independent. If you multiply the individual probabilities and it does not equal the probability of A and B, the intersection, then they are not independent, or you could say they are dependent. Okay, one does depend on the other. So we could use that type of calculation on this. In other words, if I wanted to test out whether the probability of student liking math, for example, depends on whether or not they're female, what you could do is find the probability of liking math and find the probability of being female, multiply those together, and see whether or not that equals the probability of being the probability of liking math and being female. Let's see if those are equal. Let's do that calculation and see, and we'll use that to sort of answer the question. All right, to be thorough, we would do it to all four subjects, but I think this will give us a pretty good idea. So probability of liking math. Okay, so probability of liking math, we're thinking target over total. So math lovers out of the total. So 58 out of 240. Okay, so that's 58 out of 240. Okay, now let's multiply that by the probability of being female. Target over total. Females out of total. Okay, so females are 114 of those. So that's 114 out of 240. And let's see how that compares. All right, I should put a question mark on this because we don't know if they're equal or not. Let's see if that equals the probability of being a female math lover at the same time. So that's our target, female math lovers. So there's only one cell that represents that. The female math lovers are right here. There are 12 of those. So 12 out of a total of 240. Okay, 12 out of 240. Okay, now let's see if these are equal or not. All right, so on the left side, okay, we've got 58 over 240. Okay, times 114 over 240. Okay, and that's giving us 0.1148. Okay, which is, almost 11.5%. Now, over here, in fact, I'm going to write that as a percent. 11.48%. Okay, now 12 out of 240 is 0.05. That is 5%. exactly. Okay, so we have 5% compared to 11.48%. So those are not equal. So, since the product of their individual probabilities does not equal the probability of their intersection, then that means that they're not independent. In other words, they are dependent. So does liking a subject depend on whether students are male or female? The bottom line is yes, it's dependent. And these are the calculations that back that up. All right, this video is 41 minutes long. I've done a lot of talking, which I don't like to talk quite so much because I know you guys space out. But there's just so much to cover that I felt like I had to. All right, I hope there was something in here that was helpful to each and every one of you. I will see you on the next video.